I'm going to do a quick view on PyMC3 also. So after this, you had 2 explanations. It should be really click. It should really click. About this presentation, you can download the slides on GitHub. The presentation is based on a blog post, which you can read on my website. It's more elaborate than what we're doing today, and it's all based on the paper of Facebook itself about Prophet. So Prophet is a time series prediction tool Facebook developed. I have some assumptions that you have a little bit prior knowledge about Bayesian inference. It is not needed, but yeah, you will understand it a little bit better if you do. And you're a little bit familiar with PyMC3. Yeah, so this is a slide from the paper. These are events Facebook has on a daily basis in their work. They have humanly generated data, and that's typical, yeah, a typical family of data, which has got things like seasonality. You've got weekly cycles, you've got a yearly cycle, you've got trends, things change over time. You've got dips at the end of the year, something like holidays, and you also got outliers, stuff that you don't want to model. And this is quite, yeah, there are quite a lot of aspects in this data. And handling this data, yeah, to be able to do so, you need to be quite a time series expert. You have the signal you need to explain, so you have an autoregressive part, you have a moving average part, but those two algorithms, they require stationary data, so you cannot have a trend, so you need to integrate the data. That means you need to have the current time step, and you subtract the time step before that, and if it still has a trend, you do that again, and you need to reverse that when you make a prediction, so that's also a little bit more complicated. Then you have a lot of seasonality in humanly generated data, and there's also the holiday effects, the exogenous part you need to model. So yeah, there are a lot of things you need to consider. So Facebook says, yeah, we want to do this on a more automatic way and yeah, more robust for people who just started with time series. So they came with Prophet. Prophet uses generalized additive models, which is just a fancy way of saying we take different parts and add it on in one formula. Yeah, just add different parts together, and that's our final predictions. So they say we have a trend in the data, which we want to explain. We have seasonality. We have a lot of seasonality, which we want to explain, and we want to do something with those holiday effects. And of course, we also have an error term for things we cannot explain. If we add those things together, we have our signal. At least that's what we hope to have. And they do that on a Bayesian way. They do that with Stan, which is another tool, yeah, just like PyMC3, a Bayesian modeling tool. So to be to be formal, here is the official definition of Bayesian modeling. So you have Bayes' rule, and in it you see 2 parameters. You have a theta, which stands for all the possible parameters in your model, and you have capital D, which is the data you have observed from the world. And we are interested in the posterior distribution, which is, given the data we've seen, what's the probability of our parameters of the model? We want to have highly probable parameters for our model, right? So what we're saying, we have some prior probability, we have some prior knowledge that we put into model. We think our parameters are likely to be this. And we have the likelihood function that for all the parameters, we can compute how likely it is given a predefined distribution. But if you multiply those 2 together, you don't end up with a probability distribution. That's why you need to divide it by the marginal likelihood. So it sums up to 1. Well, it turns out this marginal likelihood is a summation or an integral over all your parameters, all the possible parameters. So this is really expensive and yeah, not really possible most of the time. So that's why we use a tool like PyMC3. And PyMC3 uses a trick called MCMC, Markov Chain Monte Carlo, which samples from the posterior. It's a nice trick, and therefore we don't need to normalize. You can leave it at that for today. So yeah, I'm going to talk a bit about Bayesian in a nutshell. The Facebook uses data from American football players. I don't watch any American football. So yeah, let's say I want to learn something about American football, and I want to learn something about the lengths of the players. And say that the standard deviation is known. So I already know one parameter. The standard deviation is 5, but I don't know anything about the length. Now I think American football players are really long, so I have a prior belief that that this distribution is centered around 1 meter and 90 centimeters. So that's my prior. Then I observe two lengths of 2 American football players. One guy is 165, the other is 170. Okay, I've observed those 2 data points from the world, and given a likelihood function, let's say I think it's normally distributed, I can reparameterize 2 normal distributions and compute the likelihood of those, seeing this data. And then I can multiply those 2 together. And in the last line here, we normalize it by dividing by the sum, and then we end up with something like the posterior. And in the right, you see the posterior, and you also see the original prior and the likelihood plotted next to it. And you see that the posterior is in between. So the end result of the posterior is a combination of our prior belief and the data talking. And the more data we have, the more the likelihood will speak and less the prior. But you can see you can already make inferences with only 2 data points. So that's Bayesian in a nutshell. And there is also PyMC3 in a nutshell. Nutshell works with context managers or with contexts. I can start a PyMC3 context, and in that I can define priors. So the first line is prior, a normal distribution with a mean of 190 and a standard deviation of 5. And then I define a likelihood function, which I assume is also a normal distribution. And I think the mean of this likelihood is my prior. But then I will check with the observed data, and I multiply my prior with the likelihood. And then I can say PyMC3, the magic inference button, we heard it in the previous talk, samples for me from the posterior. And if we plot these samples, we see the same kind of result as we saw with really computing the posterior distribution. Only, as you can see, we plotted a histogram. It are really the samples from posterior, so we don't know the real probabilities, but because we have samples, we can approximate the real probabilities. So that's really cool. So why bother? Well, you can embed prior belief in your model, so you can really, I think this is really valuable. And if you don't want to, you can just have uninformed priors. Say, okay, I'm likelihood, I let you decide. You can regularize with sensible priors, because if you give a very low prior probability to certain values, then the likelihood can be high there, but a very small number versus a high number is still a small number. So the posterior likelihood, the posterior probability will still be low. And uncertainty, which is very valuable. Uncertainty in single predictions. You get posterior distributions for every prediction you make, and I think this is really important if you make business decisions. And just point estimate values, I don't know. So let's start with PyMC. No, let's start with profit. So in the paper they take some data from Pete and Manning. It's the guy looking at you. I had to Google it. He's an American football player, and these are his Wikipedia views. The first thing what we're going to do is min-max this data, min-max scale it between 0 and 1, because that makes it very much easier to think about our prior values, because we know that the data is between 0 and 1, and we can have prior beliefs of what kind of parameters our model should have. And then what we're now going to try to fit is a linear trend with change points. So we're going to have a hyperparameter, and we say there are, let's say, 25 change points in this data, and we're going to make a grid. This is something you define yourself, so this is really a hyperparameter you should tune. And what we're saying at this change point, the linear trend may change. And how much it must change is something the data can speak, or we can regularize it with having a sparse prior, saying the change points cannot change too much. So yeah, we have a base growth. We say we have some k, and if we do k times t, we just have a linear function, a linear trend, right? But we want this base growth to be able to change at every change point. So we have a vector called delta with change points adjustments. So we have s change points, that's the number of change points we've got. And we've got this vector, and then we say for every time step t, we look at, okay, have we surpassed a change point? If we have surpassed a change point, we modify the original k with the delta from the vector. So over time, the growth rate changes, right? So at every change point we surpass, we change with the delta from the vector. And if you look closely to this summation, this is actually a dot product. So we can vectorize this, which is needed to be, makes it easier to work with PyMC3, which is something, which is just computation library, sort of like TensorFlow. You need to make linear algebra formulations. So we can make a function a of t, where for every time t, if the time is larger than a change point, we say this is 1. We have surpassed this change point. If we didn't surpass this change point, this is 0. So we have a sort of Boolean array, have we surpassed this change point or not? And then we can just make a dot product with the original delta vector, the change points. And we can vectorize this even further. We can do this for all t's in the data, and then we get a matrix, which we can. So we can use this formula with one operation. Yeah. And that leaves us with this. So we have the original change point, the original growth, k plus this matrix A times delta times t. Here we change the growth rate over time. But if we only have this left part of the equation, this part, then we will not have a continuous function. So we need to offset it with the change points times s. Well, how does this look? We can make this in NumPy with some broadcasting, and then you will have this plot. Below you see the growth rate offset. So this is the offset part of the formula. In the middle you see the growth rate adjustment. So here you see that the growth rate changes over time, and we have an increasing trend. And if we combine those two plots, we will get the continuous function above. So this is a way in which we can make a growth rate plot. And you should note I've chosen some random change points here. So this is not the grid, but in the algorithm we just have a grid of change points. But you can also change it. It's up to you. And also I've used only positive deltas here. So that's why it's increasing, but it can go both ways, of course. So this part of the model we can create in PyMC3. To the left, you see a sort of a formal definition of our priors. So k comes from a normal distribution parameterized with 0 and 5. Delta comes from a Laplace. I will get to how that looks later. So given our priors, we can define the trend function, which is we've derived just earlier. And this trend function we can put into a likely function y, given the trend function and given an error term, delta, and we assume it is from a normal distribution where the mean is equal to the trend function. All right? And then we can start sampling. So what you see on the left, you see also on the right in PyMC3. So we have those, in those contexts, we have the priors, and then we define the trend function, and then we put it in the likelihood function. Yeah? That's equal. And what we'll get is this. So yeah, you see at top, you see a linear trend with a different prior. So to the right, you see the priors I've chosen. This is prior, a Laplace prior with a scale of 0.05, and this is with a scale of 0.5. So the first prior is very sparse. We have a high probability of the change points we sample or the change adjustments being equal to 0. And in the prior below, you see the change points adjustments can be quite high. And you also see this back in the plot. So the first one is much more regularized, and the second one, is really free to follow the data. I would say the first one with the regularized one is better because in the bottom one we are actually explaining recurring patterns with a linear change point trend, which should not be done. We should use seasonality for that. So so only modeling the trend isn't really forecasting because we don't know how the trend will change over time in the future. So we want to model stuff we really can be a little bit more certain about than the trend. The trend is really, I think, the hardest thing to forecast, and the noise, of course. So we need some seasonality. Prophet defines seasonality with Fourier series. Fourier series are a summation of sines and cosines, cosine functions, rescaled, and with I think you all know, you heard about Fourier transforms. We can model any function with the summation of sines and cosines. So it's really powerful. If you make the order high enough, you can model any function. But in this formula, there are two things that are hyperparameters, which is p and the n. N is the order of the Fourier series. P is the period of the Fourier series, and A and B are learnable parameters, something we need to infer from the data in our model. So here we have a visualization of that. This is P, and this changes the period of our signal, right? So now we have one sine function. So we don't plot the cosine, but it's also there. But the cosine is just offset in one phase. So you have you have both. So, and then you can also change the order of the Fourier series, and then you get just multiple sines on top of each other, and you can scale each order. So the scale part is not in this visualization, but that's something that can be done. And these are the hyperparameters that are default in Prophet. So for the yearly seasonality, Prophet has a default of an order of 10 and a period of 365 days, which is logical. So the weekly, the period is 7, and the order is a bit lower, is 3. But you can also, if you think there's a lot of things changing in your weekly data, you can increase the order, of course. But you add more variance. Well, what can we do? We can actually extract those learnable parameters, A and B, with which we scale the Fourier series and just come up with a vector where we put in the hyperparameters. So the hyperparameter 7 for weekly data and an order of 3. And then we just define this function, define this matrix, x of t, and we extract the learnable parameters and call them beta. And then we just have a dot product. Seems like linear regression, right? And we can also code this up. So here you have the same. Here you have a function in Python where you put in time, you put in the period, you put in the order, and you'll get back this NumPy array with the x's. And then you can come up with any beta and multiply it, do the dot product, and you will end up with this plot you see to the right. So that's the seasonality. Now, for the model, we made a helper function where we take in the model and we take in an argument which says I want yearly or weekly data, and we take in the prior we want to set, the prior where we define our scale parameters A and B for. And then we define this matrix X, and we define the prior, and we return this. Yeah. And yeah, so the complete model without holidays effects. I'm not gonna go to the holidays effects today because I think those are really easy to implement. It's just a linear regression with dummy variables. So the complete model is the trend, the linear trend with change points, G of t, and seasonality for the weekly seasonality and the yearly seasonality plus some noise term epsilon. So yeah, we have G from the original model we made a few slides ago. We have a prior on beta, which is pretty uninformative with a standard deviation of 10. It can be anything, we say. And then given those Fourier series matrix, we multiply with beta, and we end up with the seasonality signal. And then we can define the likelihood. We assume the likelihood to be normally distributed with a mean of the linear trend plus the seasonality. And then the standard deviation is some error term, sigma. And you see that left is the same as right? And then we take a coffee. Yeah, this takes well, half an hour if we would do it live. And what you end up with is posterior samples. Here I plotted the histograms, or the posterior samples, samples from the posterior for every parameter in the model. And you can see those, for instance, at the delta, you see this one is very, very tidy, which means we are really certain about the value of this parameter. For some, we have a more wide distribution, which, yeah, there's more variance. So this uncertainty is very powerful. What we can actually do is re-implement this model in NumPy and compute quantiles for our distribution samples. So if we do that and we plot the different aspects of our profit model, so we have the trend part. That's what you see here. We have the yearly seasonality, what you see here, and you have the weekly seasonality, what you see here. Yeah, you really, how you call it, subtracted out the different parts and can really look at them separately and think, is this logical? Is this what I expect? So it's really explainable. And you also see the quantiles of your sample points. So these are credible intervals, 95% credible intervals you see here. And it seems like at most places we are quite certain. I think this is because we have a lot of data points. But you would see if there are less data points in a certain time period, those credible intervals will be more wide. And yeah, you are more uncertain. Yeah, well, if you look at this, the weekly seasonality and the yearly seasonality is, of course, really handy with forecasting. You can just look at the time in the year and you have those values. For the trend, it's harder. If you look here at the trend, we stopped at 80% of the data, 80% of the data points, and then we extrapolated linearly to the end of the data because you can change this. This is a hyperparameter, but I would say you don't want to follow the trend that you see in one day because one day can spike and it's really not reasonable to assume that this day will spike for the next 3 months. So you take, yeah, you look at a more longer period what your trend is probably going to be and you extrapolate that. So that's what's done here. But then for every future change point, we don't want this trend to just continue because yeah, how certain are we about this? So what profit does, it isn't really Bayesian. It's just a sort of uncertainty trick, and I don't know if you can see it as I have this much chance that it will happen. But what they assume is, okay, I've seen, for instance, at every time step t, there was a probability of I've seen 5% change points in my history. Then I'm going to assume that for every future time point, there will also be 5% change points. So at every new time step, there will be a probability of being a change point, that at this point, the linear trend can change. And then also the rate of change, we're going to assume to be the same as the mean from the rate of change we've seen in the past. So in words, it's saying, okay, I expect my future to see the same rate of change as I've seen in the past. And yeah, there's not mathematical proof of this, but this is more of a, it seems reasonable, right? So with this, you get some sort of uncertainty in your trend prediction. So if you would plot only for the trend, and so we start predicting at the time you see those credible intervals. What we've done, we sample this 1,000 times. What you don't sample with Bayesian, but you just apply this formula. So you make a prediction and you look where it comes, and then you do it again, and you do it again. And if you do this 1,000 times, and then you can make some sort of credible intervals. And you see you have quite some uncertainty here. And that's also true because in the past you've seen quite a lot trend changes. And if you want this uncertainty to become less, you need to take a more restrictive prior, more sparse prior. So last things I want to say about this is that it's really quite easy to use those additive models to add new parts, new stuff. So for instance, the holidays are just a dummy variable at a certain time step times a weight you need to learn. You can also add temperature maybe, so add another time series you want to add. Just let your imagination go, and you will see something. The components are really understandable and explainable to business. Certainly with this uncertainty we've got. And the default priors of profit are pretty robust. They use it to do time series forecasting without a man in the middle. So they do it automatically, and then maybe they do some data scientists who check on later if it was okay. But they give pretty reasonable forecasting just out of the box by saying fit predict. Thank you for your time, and are there questions?